everybody. I'm Steve. Thank you so much for having me here in France. I love France. I love every chance I get to come here. This is my first time in Nantes. I'm here today to talk to you about the Rust programming language, which is the thing that I've been working on in open source capacity for about 2 years, but I've been lucky enough to have as my day job for the past year or so. And so in this talk, I hope to give you a high-level overview of what Rust is, why you might like to use it, and what it's good for. So Rust is a programming language, first of all. It's primarily about 3 different things: safety, speed, and concurrency. Now, historically speaking, most programming languages would see those first 2 things as contradictory, i.e. if you use a low-level programming language like C or C++ or something like that, you get lots of speed, but you get very, very little safety. However, if you use a language that has a higher degree of safety, like, say, Ruby or Haskell, something like that, a program that has a garbage collector maybe to help you with memory-related issues, then you have the safety, but you don't get the speed. And that's historically been a trade-off. What Rust is trying to do is to give you both of those things at the same time. And of course, you may wonder, what's the trade-off there, right? Like, you have to pay for it in some fashion. And basically the answer is that Rust is a little harder to write because the compiler enforces these kinds of safety guarantees. And so when you start programming the language, you may have a little bit of struggle getting into it or getting used to the way that you write Rust. So the programmer pays that cost up front, but then your code runs very, very fast and very efficiently, and you can be very confident that it works the way that you intended. And finally, concurrency is a very big thing in programming. As we get more and more computers with more and more cores, it's very important to have a good concurrency story. And it turns out that the safety aspects of Rust also just give you really good concurrency effectively for free. Because the same rules that help Rust be safe in a single-threaded context also help Rust be safe in a multi-threaded context. Rust has been getting a lot of attention in the programming world in the last year or 2. I've been talking a lot about it on various websites. But it's actually a project that's 8 years old. So what's funny is when you've been involved with Rust for a long time, like me or some other people, there was a discussion as we reached 1.0 recently, which I'll talk about in a moment, about like rushing to ship the 1.0 thing. But for those of us that have been around a while, we're thinking, we've worked on this for 8 years already. Like, it's time to actually ship something useful. So for the first 4 years of Rust's life, it was a personal project of Graydon Hoare. Graydon has worked on a number of software projects. You may have seen his name in other contexts. And then eventually, he was working for Mozilla at the time, and about 4 years in, Mozilla took it as a project, as a Mozilla official project, and started paying him to work on that instead of what he used to work on. And then, more recently, Rust has sort of evolved, and we've done this 8-year-long process of try new features, see what works, see what doesn't, throw out the bad ones, put in the good ones. The reason that Mozilla cares about Rust is because Firefox is written in C++, a couple million lines of C++. And that's necessary because writing a web browser requires high degrees of performance. But C++ is a programming language that, for good reason, mind you, has a lot of weird edge cases and corner cases and is a very, very sharp tool. And C++ programmers cut themselves with this sharp tool quite often. About half of the security vulnerabilities that we've seen in Firefox recently are basically C++ programmer errors, and that's sort of what leads to this kind of situation. And so Mozilla decided to develop Rust in the hopes of making Firefox both more secure and faster at the same time. Towards that aim, they've been working on a web rendering engine called Servo. So similar to how Gecko is the rendering engine that powers Firefox, Servo is a web rendering engine that's been written in Rust. And that's really helped us focus the language and make sure that it's useful for building actual real-world applications instead of just compilers. The Rust compiler is also written in Rust, but if it's the only thing that your program is, only big project that your programming language is used for, then you end up with a programming language that's good at writing compilers and not necessarily one that's good at writing more usual programs. So it's not intended that Servo will replace Gecko inside of Firefox. If Servo becomes a product, it will probably be a different browser altogether. However, a couple weeks ago, Firefox's build process actually gained the ability to build Rust code. And there's a patch that hasn't been applied yet, but it uses Rust code to do all the URL parsing stuff in Firefox. So that's likely that what's going to happen is that parts of Firefox will be rewritten in Rust. Maybe there will be a new browser built on top of Servo. We'll sort of see how that goes in the future. Okay, this quote is a little small. Why bother programming in Rust? I think that the biggest reason to program in Rust is this quote from Alan Perlis. And he says, "A language that does not affect the way that you think about programming is not worth knowing." And so Rust has a bunch of really interesting concepts, but primarily there's one or two big ones. When I was putting this talk together, I sort of decided, should I talk specifically about the one feature that makes Rust the most unique for 30 minutes, or should I give a broader overview? And I figured talking for 30 minutes about one concept might be a little too overboard, so I'm going to go with a slightly larger overview in this talk. We'll talk a little bit about that central concept in a moment. But Rust really changes the way that you think, and a lot of people describe programming in other languages after they've gotten comfortable with Rust as it making them program things better in other languages. That particular feature that I'm referring to is called ownership, and there's two sub-features of that called borrowing and lifetimes. And basically what this means is that in Rust, it gives you sort of the low-level pointer stuff that C and C++ have, but the compiler knows where those pointers are valid. So one very common error that happens in languages with manual memory management is that you'll allocate some memory, make a new pointer to that memory, free the memory, and then use that pointer that's pointing to now invalid memory. So Rust compiler is able to track the lifetime of those pointers and make sure that your pointers are never pointing to invalid memory, which is really, really huge and causes, even if you're not doing that pointer stuff directly, it causes a number of secondary errors with things like iterator invalidation, which are based on the same root cause, even if they're like different problems as far as the programmer goes. The second reason why I think that you should learn and care about Rust is that I think that Rust has the power to become a lot of people's first systems programming language. And it's really funny, we as programmers talk about something being hard or something being easy with terms of programming, but we all are different kinds of programmers and different kinds of people, and our brains think about code in different ways. So for example, I know people who think that web programming is far too difficult. They would much rather prefer programming in assembler. They're like, assembly instructions do one very specific thing. I know exactly what it's going to do. You embed a markup language and a styling language and a Turing-complete programming language and then ship it to another computer on the other side of the world running a completely different operating system, and you still expect that to work? That's too hard. I don't want to do that. And so we sort of talk, a lot of people, or at least the programmers that I talk to, talk about low-level programming as being difficult, and I think that scares away a lot of new programmers from trying out this sort of systems and low-level programming tasks. And I think that's really unfortunate because they're really fun and cool also, and some people are much more into those. And so Rust is a particularly good programming language to learn systems programming with because the compiler is there to help you. So all of those checks that help seasoned programmers program correctly also help inform new programmers of the kinds of patterns that will make them not screw up. There's some people that think that you should learn C before you learn Rust so that you feel the pain of having to deal with bad C code before you learn what Rust saves you from, but I don't really believe that you have to deal with pain in order to enjoy things. I prefer skipping straight to the enjoying things. So, and we specifically in Rust are very interested in bringing new people into systems programming in general. So for example, there's an entire chapter in the online book I'll talk about later that I wrote about the concepts of the stack and the heap. And that's a general programming concept. It's only directly related to Rust in the sense that you need to care about it when you learn Rust programming. But if you would pick up a like C++ textbook, they would refer to the stack and the heap and assume that you already know it. Since most programmers that work in a managed programming language like Ruby or Java don't have to care about the stack versus the heap, we think it's really important to explain these kinds of base-level computer science concepts that you may not know if you've never done low-level programming. So we're really, really interested in having Rust be your first low-level programming language as well. Okay, what's funny is I left this slide this way, so you may see my bullet points are slightly screwed up. I actually generated this presentation using Rust's documentation generation tool, which allows you to embed arbitrary HTML and CSS, and so it spits in the HTML and the CSS stuff to make a presentation instead of like API documentation. But apparently there's still a little bug I haven't sorted out yet, so I decided to leave it in as kind of charming. But you know, technically the bullet points are a little off. So Rust also has this reputation of being a programming language that has changed a lot. Like, your code will not compile tomorrow a lot. And part of that is because we wanted to make 1.0 as good as possible. And we knew that after 1.0, we couldn't make any more breaking changes because no one wants to learn a programming language they have to relearn next week. It's absurd. It was my day job, and it was difficult for me to keep up during the last couple months of Rust's development because it accelerated at such a great pace. But now that we shipped 1.0 a couple weeks ago, we're making this guarantee that Rust 1.1 will compile any of your code from Rust 1.0, and Rust 1.2 will compile any of your code from Rust 1.0 and 1.1. And that's also really good because we're releasing those point versions every 6 weeks. This is inspiration taken from web browsers themselves. So web browsers need to build in new features, but they also need great stability. And so you can get a new version of Firefox or Chrome every 6 weeks. Most programming languages ship, if they ship fast, on a yearly schedule. But there's some problems with that in that if your feature is ready in October, it's going to get significantly less testing than if it shipped in February. Like in Ruby, we ship on Christmas, so I'm used to thinking things in the calendar year terms. And so if your thing ships, say, December 1st, you really, really want to sneak that into the release, because if it doesn't get out, you're going to have to wait a year for it to show up. But then you only have a month to make sure that it works. So by pursuing this sort of aggressive schedule, we hope to have a higher quality of features because we don't have this pressure to shove everything into the release right before the end. It's no big deal if it doesn't make it into this particular version of Rust. It's just 6 weeks until the next one. And so that stability aspect and this upgrading aspect is very important to how we're doing things. Okay, so to give you a slightly more concrete example of the kinds of safety problems that Rust saves you from, I'm going to show you a little teeny bit of C code. And then we're going to talk about Rust features and sort of what Rust feels like in a bunch of different ways. I'm going to show you a bunch of code samples. So here is a very simple program in C. And it's not a particularly good program, and one of the problems with showing examples is that many people who are experienced C programmers would say, I would never write C code like this. And it's true, but I can't show you like a million lines of C code on the screen either for a realistic example, right? So just bear with me in that examples are not representative of real code, even though they may represent real problems. So this allocates a char star, a string, and makes a pointer to it called S, and then it attempts to set the first character of S to H, a capital H rather, because we had a lowercase one, we're going to fix it to capital. So this is okay, but there's sort of problems with how this works. Because, for example, in this case, it's allocated statically. It's not like dynamically allocated. So it's in a read-only memory segment. And if you run this, your code will actually segfault because it's a read-only string and you're modifying it. And segfaults are, you can track segfaults down, but you only get them at runtime. The compiler does not help you with them. And, in this example, it's pretty easy to figure out where the problem is. But things that cause segfaults can happen far, far away from the actual code that you write. In Rust, the equivalent code, which looks something like this, will give you an error. Type &stir cannot be dereferenced. And the reason that this happens is because it knows that you're not allowed to dereference a thing of this particular type and modify it. You would also get an error about mutability if we got farther than that, if we changed the types to make it work. Because Rust defaults to immutable by default. So this is a very trivial example of the kind of problems that Rust saves you from, but it turns errors that are runtime errors into compile time errors, which is significantly nicer. And we'll talk about that at the very end, actually. Okay, so enough about those kinds of silly problems and just this general idea that runtime errors in low-level programming languages turn into compile time errors in Rust. I don't like to talk trash on other programming languages, even though you're improving other languages, so that's the only thing I'm going to say about other stuff. We can talk more about details if you talk to me later in this conference, but now I'm just going to show you good Rust code. So this is Hello World. Not particularly exciting, but I think I'm legally required to show you Hello World at the beginning of presentations about new programming languages. There's some subtle things here that are kind of interesting, though. One of them is that our declaration syntax is a little different than you may be used to. You'll see we use the FN keyword. I like to joke that fun, while kind of fun, is a little awkward. And we learned from JavaScript that typing function all day is not any fun either, so we went with FN. Most Rust keywords are a little shorter, but you type FN all the time. Secondly, you'll notice that unlike some other programming languages, we don't do the return type, function name, arguments type. Instead, main doesn't return anything in Rust, so there's no return type, but if there was, it would go after, and you'll see an example of that syntax in a moment. But this seems like a trivial syntax change. Why not just stick with the way that other languages do it? But what's cool about this is if you want to know where a function is defined in a Rust code base, you can grep for FN name of the function. And it doesn't matter if it's a method or some other type of complicated function declaration. It'll always look exactly like that. And so we chose a lot of the syntax stuff. It's not just change for the sake of change. It's for things like grepability. Println. Println has a bang on the end of it, and that's because it's a macro. So in this case, we're not actually interpolating any variables. You'll see that in a minute. But Rust does compile time checking to make sure that if you say, I'm going to put a digit inside this string, you're actually passing in a digit instead of some other kind of type. So at compile time, there's these macros that let you do that kind of compile time compilation. And we use the bang to signify that it's a macro because you want to know that this may be doing something more complicated than a simple function call. Here's a slightly more complex example that shows off some more advanced features of Rust. We'll go over the syntax very briefly, and then I'll talk more in detail about these features later in the examples. I left a use standard thread at the top of this one because I'm going to introduce threading very soon, but you can import aspects of the standard library with a use statement, and then this creates an array of 2 integers, and then makes an iterator out of them, and then calls map. Now, this is kind of a bog standard feature of programming languages, so it's kind of boring for me to be showing you this, especially if you've been working in a functional language. But the reason I wanted to show you is because Rust uses LLVM on its back end, and LLVM is amazing and magical, as I like to say. And so this particular map is lazy, so this won't actually evaluate to anything. But if we were to do something with nums, like we will in a moment, Rust actually knows how iterators work, and so it's able to generate LLVM IR that compiles down to a very efficient for loop. So for example, if you think of a naive way of compiling this code, you would think, oh, I'm passing a closure to a function and then iterating. That's got to be very expensive. But LLVM is actually able to analyze that this does not capture over any external variables, and therefore it's able to collapse the closure into a regular function. And then it knows how iterators like map works, so it's able to actually compile this down into the same assembly that it would generate for a for loop. So you don't pay anything for this extra level of abstraction. You get to write the nice functional looking code, but you get the same assembly as if you wrote the low-level dirty imperative code. And this is a really important aspect of Rust and sort of where it gets some of its functional-ish kind of heritage from. The original Rust compiler was written in OCaml, and so we take a lot of things from functional programming languages. A significant number of Rust people used to program in Haskell. We haven't quite gotten onto the Haskell level of ridiculous type system stuff yet, but generally speaking, you get to write high-level code, but it compiles to the same efficiency that a more low-level implementation might do. Okay, so references. Rust has this concept of references. This is a sort of a silly example to show you the very basics of the syntax. So this +1 function takes a reference to an integer and returns an integer and just adds 1 to it. And you can see function calling, and we pass in &5. This looks pretty easy, and it is pretty easy. But the thing is that if in more complicated examples, as I mentioned before, Rust has this ability to track where your references are valid or not. And so if this is a more complicated type, and we'll get into some of that in a moment, Rust is able to make sure that this pointer is always valid for the lifetime of the pointer itself. I just wanted to show you mostly the return syntax and what references look like. There's not a whole lot else interesting in this example. So boxes. Boxes are the basic way that you allocate something on the heap instead of the stack. So I don't have time to get into that distinction, even though I alluded to it a little bit earlier with that chapter in the book. But the previous example used a 5 that was allocated on the stack and then passed a pointer to the stack to the other function. Box allocates something on the heap and lets you pass something to the function. So the interesting thing about this, you'll notice, is that we don't actually call free here. So box internally is able to call malloc to dynamically generate but get some memory from the operating system. And then what happens is the compiler knows when X goes out of scope, and the compiler will insert the call to free for you. So it's not possible to accidentally not free this kind of memory. There are certain situations in which Rust will leak memory, but that's sort of off topic for this particular instance. But in this case, it will not leak because the compiler does this for you. And this is really, really nice. It also makes sure, for example, that if the function +1 did not return before the end of main, it would give you an error saying, hey, this is going to free some memory, and you're accidentally going to be accessing it, and all this kind of thing. But this is sort of what I mean by Rust doesn't have a garbage collector, but it doesn't really do manual memory management either. It's kind of like automatic compile time memory management. And that's one of the things that makes Rust kind of interesting and feel a lot more high level, because you're not worrying about when do I need to free this variable. You just work with your code, and the compiler will tell you if you're doing something that would be unsafe. All right, this is the slightly longer example with threads. As I said, concurrency is very important. One other aspect I do want to call out here is that you'll notice we say use standard thread. I mentioned earlier use lets you bring things in from the standard library, but threading in a language that's as low level as Rust is actually entirely a library concern. And so you can actually write alternate threading libraries And what's cool about that is it means that the same safety we have for threading in the language proper can be used for any libraries you write. So for example, the Rust standard library only includes blocking I/O, so you block threads whenever you get I/O stuff. But because it's all libraries, there's people that are actually implementing alternate I/O libraries that do non-blocking I/O, and I'll show you later it's really trivial to bring in alternate packages. And those libraries have the exact same safety properties that this built-in stuff does, which is really, really neat. So in this example, we have some numbers and we have some names, and then we generate that iterator to get a particular number, odd numbers out of these even numbers. And then I'm not going to get too deep into the syntax, but thread spawn allows you to spin up a new thread, and then the double pipes and the curly braces are a closure syntax. So we're passing a closure to thread spawn to actually generate, and that closure gets run in this new thread. I don't have time to talk about the move keyword, but that's kind of semi-important in this particular example. But so this then prints out the index of the numbers that are generated from the iterator to the array and prints out a thing. It's just a very simple example. When we sleep for 100 milliseconds so that we let our threads run, these prints will run very fast. So we pick a number that's relatively small, but that way we can let them finish generating. So this will spin up 2 separate threads and run them, which is kind of neat. We also have channels if you want to use channels to communicate. But due to Rust's safety guarantees, using shared memory is actually not as scary in Rust as in many other languages, but channels are a really nice way to program with concurrent code, so we have channels in the standard library. This example spins up a channel with a sending and a receiving end, transaction and receiver, TX and RX, and then we pick a closure, we make a stack variable in that closure of 5, and then we send a copy of that variable down our channel. Back in main, we receive recv on that channel, and unwrap basically says throw away any errors, and if you get an error, crash the program. Since this is a demo, I'm not doing great error handling, I'm just saying crash. You could handle that more responsibly, of course, if you're writing a real program. And so we wait for something on the end of the channel and then print it out. So you'll notice here we don't need to sleep to let the thread finish because, of course, we're using the channels to make sure that we block until that thread is done completing. So this is kind of relatively basic, but I have one safety example here too. So if we instead of just computing a 5 in the thread and passing it back, say we were going to use this closure to actually capture a reference of some kind. So in this example, I've added 2 lines. X is now, again, a box with 5 in it. So this 5 is allocated on the heap instead of on the stack. And then we add 5 plus the value of X. So we'll get 10 when we print this out. But as we know, concurrency is very tricky in programming languages, and it's very hard to get it right. And so if we were to try to, say, use X again after we passed it to this thread, in most programming languages, this would give you weird results. Like, if the code after the thread spawn executed first, you might see 10, and then the thread would add 5 to it, and you get 15. In other executions, the thread might run first, it would add 5 and give you 10, and then print out 10, so you'd get indeterminate results here. But Rust actually knows about thread safety, and so you'll get 2 different kinds of errors out of this code. I have a big giant error block here. The Rust compiler gives you very helpful errors, but it means they're also very long. And we're actually working on improving them, and there's a whole number of things that go along with that. But basically, Rust says error use of moved value X. X moved into the closure environment here because it has this type of closure, which is non-copyable. So basically what it means is when we tried to add 5 onto the value of X, it said, hold on, buddy, you passed that to another thread. It got moved to that other thread. So that reference is now invalid. You're not allowed to use it anymore. And this ensures that you don't have these kinds of weird bugs. If you need to access something from 2 different places, there's a different library called, you can wrap in that to put in a mutex or something to make sure that you have this deterministic aspect to what you're doing. The second one is something I didn't explicitly mention yet, but you can't assign to an immutable variable by default. So Rust variables are immutable by default, and we found that the vast, vast majority of variables in real Rust code bases are actually immutable. And this helps greatly with concurrency and speeding up compiling and doing all that sort of stuff. Optimizations work much, much better on immutable data than mutable data. So we're able to optimize aggressively since the vast majority of things in Rust are immutable. We have this feature called pattern matching, which you may have seen in functional programming languages, but if you're not used to it, it's kind of cool. What it lets you do is you say match, and then you provide some sort of value, and then you can put things that have that value on the left and an arrow and the thing you want to do on the right. So this is kind of like a case statement in more imperative programming languages, but there's two cool aspects of this. The first is you can do more complicated things than a simple case. So for example, we can match against a single value, or 1 or 2, or even against a range of values. But the thing I like most about match is that it's exhaustive, and what that means is that the compiler knows the type of the thing you're trying to match against. And so it can actually tell you if you've forgotten to handle a particular value of that type. So in this instance, my number is an integer, say an I32. And so if we left off this last line with the underscore, which underscore means match any kind of pattern available, Rust would actually give us a compile time error saying, hey, you have a non-exhaustive match. You need to handle all of the other numbers an I32 can handle. And that's why we need this underscore here. But so it's really nice for checking. The next example I'm going to show you gives one example of where match is exhaustiveness really helps with safety. Option. So Rust does not have the concept of null. It's not built into the language. You can't get nullable anythings. However, we do have a type called option, which you may have seen from functional programming languages. And what that lets you do is that lets you say this type may exist or it may not. It may be some value or it may be nothing. And so with this, because it's a distinct type from whatever the type of the thing it is that you're using, you have to use something like this match to unwrap that type. So if you want to get access to the internal number, you use map to say, hey, if there's some value, then I want to use this value. But if there's no value, do something else. And this means that you're guaranteed to automatically handle any case in which a value may or may not exist, which is incredibly, incredibly useful for producing reliable software. Because we've encoded this concept of nothingness into the type system and then forced you to deal with it. Unfortunately, it means that this is a little more complicated than like in Ruby, I could just literally do whatever and it'll let me run whatever code I want. But then eventually that code makes its way to production and then you get some no method error on nil. And so Rust makes you handle that up front. And we have some extra machinery in more complicated cases to make it a little simpler. You'll notice earlier I used that unwrap method. So that unwrap method basically boils down to sum, return the value, else crash the program. And so we have these kinds of higher level things that let you don't have to literally write out match every time, but we do force you to deal with that possibility in whatever way makes sense. I mentioned closures a little bit before. Here's a very simple closure that we can then pass to another function, and we sort of covered that, but you see those pipes again. And since we only have one expression here, I left the curlies off, but you can sort of assign closures to variables, pass them around, do all kinds of things with them, and that's really useful. We have generics, like most statically typed programming languages do these days. And so this particular function foo has two generic types, A and B, and it takes two values, one of A and one of B. This on its own isn't too exciting. We'll talk about traits first before I get into something more interesting with generics. Okay, we need to talk about structs and traits together. So what Rust does not really support classical object-oriented programming. There's no object thing in Rust. We do let you define structs, which are exactly like C structs. They give you the ability to find some sort of aggregate data type. So in this case, this is a time bomb with one particular value of explosivity that's a number. And then there's a trait in the Rust standard library called drop. And traits let you add behavior to structs. So the drop trait is what's used for a destructor. So it says when this value goes out of scope, we're going to call the drop method of the drop trait on whatever thing it is. So this is basically defining a destructor on our time bomb that says for underscore in range of 0 to the explosivity, print blam. So if you have a time bomb with 5, you get 5 blams out. If you get a time bomb with 10, you get 10 blams out whenever it goes out of scope. But this separation from data and like methods and behavior is really, really useful because it lets you parameterize generics over this kind of trait. So you can say, I have some trait foo, it implements a method bar. This function will accept any value that implements the foo trait. And that gives you this sort of very dynamic feeling, not quite duck typed because you have to explicitly specify the traits, but you can sort of very dynamically define different things. So here's a sequence trait that defines one method length. And then when you implement a sequence for a vector of t, so vector is sort of the heap allocated array type in Rust, we can say that the length of the sequence is equal to the length of the vector. It's a trivial implementation, but I only got 30 minutes, so can't do it that much more. But this is sort of the idea, is that you implement traits on structs, and that's how you get sort of this OO kind of feel. You can do really ridiculous things with traits and things I don't necessarily recommend that you do. I come from Ruby world where you monkey patch everything, and that is terrifying. So of course I wanted to see if Rust could do that. This example wasn't actually created by me. It was created by Yehuda Katz. But in theory, you can actually you can implement traits for structs you don't own. So but you can't implement foreign traits for foreign structs. So numbers are in the standard library, and if I were to say, for example, define a trait called time, I could implement that trait for I32, and then I could say 2.days from now, and it would generate a timestamp. I'm definitely not saying you should do this or that this is good Rust code. I'm more saying this is the flexibility of Rust and how far you can go with these kinds of things. The other thing that makes this significantly more safer than something like monkey patching in Ruby is that you'll notice I had to use active support time. So if I did not use time, this method would not be available on integers. So that means that if I add some sort of method to my internal code, I can't screw up your internal code. Your library is not going to suddenly all of a sudden gain a .now method. I can keep all my mistakes and terrible code to myself and not affect you with them. So it's significantly safer. And basically the way that this works is there's some sort of trait called period that implements seconds and minutes, and then we implement that on uint and print out the kinds of things. And Okay. Another thing that makes Rust really awesome is that we have a really fantastic FFI story in both directions. So it's really trivial to write code from Rust that calls into C code, but it's also really trivial to write code from any language that knows how to call into C. It can call into Rust as well. So this is an example of the first part where we call into a library called Snappy. And so you sort of give this annotation of, I'm going to link to a library named Snappy, and then in an extern block, Snappy defines some function called Snappy compressed length, and it has this type signature. And then with just this one little annotation, you can call that Snappy foreign function in your Rust code. There's one little tiny detail that you can see here. I have to wrap that call in an unsafe block. So Rust has this, so safety is really nice and it's really comforting, but every once in a while, especially when you're doing really low-level programming, you need to do something that the compiler cannot prove is safe. And so Rust has this concept called unsafe that basically says, hey, compiler, I got this. I'm going to enforce the rules even though you can't prove them. And it's really important this is a language feature, because what it lets you do is it lets you audit the particular areas where you've done something dangerous. And it also doesn't turn off any safety checks. It allows you to do a couple of extra things. And I don't have the time to get into all of those details right now, but basically what this allows us to do is it allows us to write library code that uses unsafe internally, but provides a safe abstraction to actually using that code. So for example, that box T that you saw earlier is implemented internally using unsafe, but its public interface is entirely safe. So as a user of box, you have no way of screwing it up. It's just the implementer of box could possibly cause a bug. And this is necessary with the FFI because C code can do whatever the hell it wants, right? So that's terribly unsafe. So we need to mark all calls to FFI with unsafe. And what happens is when people write idiomatic Rust wrappers, they basically write a safe interface around those unsafe FFI calls. So for example, here's an example of doing that, where we have a pubfun validate compressed buffer that's completely safe. It accepts a Rust type, and then it does the machinery to convert it to calling to C. In this case, the danger in calling the validate compressed buffer is that the length needs to be the accurate length of the array. If we called it with too big of a length, then it wouldn't work. So in this case, the Rust type knows the length of itself, so we can verify that this call is safe in all instances, which is why we're able to just wrap it in unsafe and not do any additional checking. And here's an example of a slightly more longer function. I kind of wanted to put this here just to show you what Rust code sort of looks like. I don't have really time to get into it, and I'm sure that you don't know the Snappy compression library off the top of your head, so it's not even that useful. But this is just an example of a longer function and what it kind of looks like when you're actually writing real Rust code. And what this FFI means, and I think this is really important for the future of Rust, is that you can embed Rust in other languages really easily. So for example, one of our first production users is Skylight.io. They sell a performance monitoring thing for your Rails app. So you gem install Skylight, and then it analyzes your Rails app and sends metrics back that you can look at this nice fancy dashboard. They actually implemented that Ruby gem in Rust. And the reason is that implementing the gem in Ruby had a number of different problems. First of all, when you're measuring performance and your garbage collector stops your performance measurement in the middle of a measurement, you get really weird long spikes, right? And you can do some tricks to get around that, but then you're fighting with the garbage collector basically to make sure that it's not going to interfere with your timings. Secondly, they had memory leak issues and all these other things. So they actually wrote the Ruby gem in Rust, and now it uses basically no memory and runs really, really reliably. And so I think that there's going to be a lot of people who come from Ruby, Python, JavaScript, Perl, all sorts of other languages where, in Ruby world we say, I'm just going to drop down into C when I need performance, but then C is terrifying, so we don't actually do it. And I think that dropping down into Rust is a very viable future path for anyone that's looking to get a little extra oomph out of a particular library in their application. So maybe you won't write your entire thing in Rust, but you'll prototype it in Ruby and then find that there's a particular set of functions that need to be fast, so you write those in Rust instead and then provide a Ruby gem that makes them happen. I think it's a big area. Another example where scripting languages have influenced Rust significantly is Cargo. When I was a big proponent of Cargo existing, and some of the other core team members were very skeptical at first. They said like, "Oh, that's cute, Steve. You can use this tool you're talking about. We'll still use makefiles." And then once we built Cargo, they were like, "I'm never using makefiles ever again." So Cargo is something that's not particularly exciting if you come from the Ruby, JavaScript, Python world, but is incredibly exciting if you come from the C and C++ world. Basically, Cargo gives you the ability to download and manage dependencies and their versions, and also build your project. So Cargo new will generate a new project, and it generates just a hello world for you by default. So you can see I cd into that directory, type cargo run, and it prints compiling your file, and then I'm running the binary, and you get hello world out. There's this TOML file that we decided to use. I could talk for half an hour about why we chose to use TOML instead of other formats. I won't get into it. TOML is not spectacular, but it's the least bad format for our use cases. Yeah, I'll just leave it at that. So we have this metadata file called cargo.toml, and it allows you to specify, in this case, it actually Cargo auto-generated this cargo.toml for me based on my Git information. So there's HG plugins and other stuff too if you use a different different VCS than Git. But by default, we sort of use Git. And so this sort of gives you the package name and my name and that sort of stuff. But what's really cool is when you need dependencies. So if I want to use the regular expression library, for example, I can add a new dependencies section and say, I depend on regex of this particular version, and then I don't need to do anything else. The next time I run cargo build, of course I would use regular expressions in my code, right? I would actually write that up. But other than that, the next time I type cargo build, Cargo detects that you don't currently have regex downloaded. It grabs the registry, looks for the latest version that I specified, downloads it. It downloads its sub-dependencies. So you'll notice that regex has a dependency on regex syntax, so I didn't need to specify that. It just grabbed the compatible versions for me, links them all together, and compiles my project. So this is like light years away from dealing with Git submodules inside of makefiles, which are two things I never want to do, but want to do together even less. So this is a really, really nice thing. This is a big, giant block of text that I'm not going to read all of you, but we've had some people start to use Rust in production now, and this is a testimonial from one of our production users. So they moved from C++ to Rust. And a number of things that they had to say were, we have performance, increased safety, modularity. In addition, we found something even more significant, first time working code. Our last library that we wrote in C++ for our UDP was a 5-month job to remove data races, but as soon as it compiled in Rust, it was data race free. Also, one other thing I want to mention briefly, I found an interesting thing here. Ruby, Python, Java, and C# programmers just take to Rust instantly. And C and C++ developers actually take a huge time to transition because they have to unlearn fear, which I thought was a very interesting statement. They had a 500,000 line codes, 500,000 line of C++ code base that did a version 2 in C++ again, and it was 75,000 lines of C++. And then they saw Rust, and they're like, I wonder how far we can get in a weekend. And then they rewrote the entire thing in a weekend in like 8,000 lines of Rust code. So they've been very, very happy with Rust. OK. I'm out of time, so I can't give you any more examples right now, but I want to point you to some things you can do to learn Rust in the future. There's 2 great projects we have officially. One is the Rust programming language, which is a book that I offered. It's about 250 pages currently, and I'm still adding more stuff, so lots to learn there. And then Rust by Example leads you through bite-sized examples of learning how to program with Rust code. So those are the 2 big things. We have a number of different forums in which you can discuss and interact with other Rustations, as we call ourselves. So there's 2 different forums, the users and internals, one for developing the language and one for users of Rust. There's a Reddit, which I really hate Reddit, but there's a lot of people on Reddit, so what are you going to do? There's an IRC room called Pound Rust, and there's a number of secondary rooms for specialized learning, and we have a blog series called This Week in Rust that describes things. You can find the Rust project at rustlang/rust on GitHub, and thank you so much for coming to my talk. I hope that you enjoy Rust if you pursue it in the future.